Welcome again to the second week of the live session on the course Integral Transforms and their applications. So last week we have discussed some problems on the Fourier transform, how to evaluate some Fourier transform and how to use their properties and all. So do you have any doubt in that section? If any doubt you can ask so that I can try to answer them, or you can wait until the end of this session. That's why I'm asking now. If you have any doubt, I can start them, or we'll wait until the end of the session for those specific questions. So else I will today I will discuss about problems on Laplace transforms. So regarding Laplace transform, if you have any doubt, stop me in between. I will try to answer. So before going to Laplace transform, I have one problem from Fourier transform. So evaluate the following integral, which is integral 0 to infinity sin x by x the whole square dx using Parseval's theorem. So we have 4 options here. So you can try for a minute. It's easier to do. So then I will start explaining. So meanwhile I will write what is Parseval's theorem. So if you have function f of x and another function g of x, integral of their product from minus infinity to plus infinity is equal to let's say the in general we will say it's complex conjugate of g of x. So then the integral of this product from minus infinity to plus infinity will be also equal to the Fourier transform of f, that is capital F, in the Fourier domain K, times the Fourier transform of g, which is capital G, its conjugate, again integrated from minus infinity to plus infinity. So this is not actually Parseval's identity, it's called a Planger's identity. It's a special case when f is equal to g. That's in that situation we'll know f of x into g of x, the conjugate, is equal to f of x times f of x conjugate, which in general is absolute value of f of x squared. So we are here looking at functions which are real valued functions, like f and g are real valued. So we don't need to consider the absolute square. It will be just f of x square only. Yeah, one answer is there saying D is the answer. Let's see. So any other answer? I'll wait for a while. Okay, now we can start doing the problem. So first of all, using Parseval's identity, so that is f of x squared dx integral minus infinity to plus infinity is equal to Fourier transform of f, that's capital F, squared dk integral minus infinity to plus infinity. So here note that the function f of x squared is equal to sin x by x the whole square, right? So that means f of x is equal to sin x by x. Okay, sorry, I made a mistake in the question. So there is a sin ax. Okay, so that's how the a comes in the option. All the options there is an a, right? Sorry, I missed that a. So yeah, the function is actually sin ax by x the whole square. So that means f of x is equal to sin ax by x. Okay, also so then we can apply equation 1, that is Parseval's theorem, that is the integral minus infinity to plus infinity sin ax by x the whole square is dx is equal to, let's say, the Fourier transform of sin ax by x that we don't know, we need to evaluate in the variable k, which is squared dk minus infinity plus infinity. So this is equation 2. So if we know the Fourier transform of sin ax by x, then we can evaluate this integral. So first we go into find what is the Fourier transform of sin ax by x in the variable k. So by definition, it's actually square root of 1 by 2 pi, 1 by square root of 1 by 2 pi. Sorry, it's actually square root of 1 by 2 pi. Minus infinity to plus infinity, the function sin ax divided by x, then e raised to minus ikx dx. So now what we are going to do is that we can expand the e raised to I theta using de Moivre's theorem. It's like 1 by square root of 2 pi minus infinity to plus infinity sin ax by x cos kx minus I sin kx dx. So now we distribute this bracket. It's like 1 by square root 2 pi minus infinity plus infinity sin ax into cos kx by x dx, then minus I times this I we are taking outside because it's a constant, minus infinity to plus infinity sin ax into sin kx by x dx. Now note that the function here is actually an even function, and this one is actually an odd function. So that means the integral over this odd function from the interval minus infinity to plus infinity is actually 0, and only the integral over even function will exist, and that we can also simplify like 1 by square root of 2 pi 2 times integral 0 to infinity sin ax cos kx by x dx. So this 2 I will bring inside. Now we will use 2 sin a cos b formula here, like 2 sin a cos b is equal to sin of a plus b plus sin of a minus b. That we will use here inside the integral, so that it is sin of ax plus kx, that is a plus k times x, plus sin of ax minus kx, which is a minus k times x, the whole divided by x integral dx 0 to infinity. This also we can split into 2 separate integrals. It's a sin of a plus k times x by x dx integral 0 to infinity plus sin of a minus k by into x by x dx integral 0 to infinity. So now I guess you know that this integral sin of, let's say, a number alpha x divided by x dx integral 0 to infinity. Do you know the answer of this integral? Anybody know? You can answer either in chat or you can unmute yourself and tell. Okay, this is actually a standard integral that should be well known. So its value is pi by 2 for any value of alpha, a real alpha, and also if it is greater than 0, and it is minus pi by 2 if alpha is less than 0. So this in general we can say it's actually pi by 2 times sine of alpha. Sine function, I think if you have watched the lectures, there is an explanation for sine function. It's the signum function. Basically, if you plot alpha versus sine of alpha, when alpha is less than 0, its value is minus 1. When alpha is greater than 0, its value is plus 1. Just indicating whether it is sine is negative or positive. So that is a sine function. So that we can use here to generally write the expression for this integral. So if we use that here after this particular integral, so it's actually 1 by square root of 2 pi into sine of a plus k. Note that a and k both are real numbers, plus sine of a minus k. So we got the integral or the Fourier transform of sine ax by x here. Now our objective is that our basic objective is evaluate this integral. For that we use the Parseval's theorem to obtain equation 2, that if we know the Fourier transform of sine ax by x, then square it and integrate it from minus infinity to plus infinity, we will get the answer. So now that we know the Fourier transform, we will square it and integrate it. So the integral we want from from equation 2, it says that the integral we want will be okay, I missed actually. So see that it is actually pi by 2 times sine of alpha. So I only put the sine of each alpha values here. I forgot to put pi by 2, which is common for both of the integral. So that also we need to I just forgot to put that. So if we simplify now, we will get this Fourier transform is square root of pi by 2 root 2 into sine of a plus k plus sine of a minus k. Okay, so now from equation 2 we have the integral that we want will be actually equal to minus infinity plus infinity integral square of this term, square of the Fourier transform of sine x by x. So if we square that, the constant I am taking outside, root pi squared is pi divided by 2 root 2 squared is 8 into sine of a plus k plus sine of a minus k, which is squared dk, integral minus infinity to plus infinity. So now we expand the terms inside the integral using binomial expansion. It's sine of a plus k squared plus sine of a minus k squared plus 2 sine of a plus k times sine of a minus k dk. Okay, let me erase some parts in the top so that I can finish everything in this page itself. So yeah, now if you see it's minus and plus infinity, sine of a plus k squared. So if you see, sine can be plus 1 or minus 1. When it is squared, it will be actually plus 1 always, right? So that is the first time is plus 1 always, and sine of a minus k is also going to be plus 1 or minus 1, but when it is squared it will become plus 1 always. So 1 plus 1, so that I will write it as 2 together. I'll write 2. Then the third term here, that is 2 times sine of a plus k times sine of a minus k dk. So both of these terms has a common 2, so that 2 I am taking outside and writing here. So this 2 will cancel with 8, so that in the denominator 4 will come. Okay, so now we need to know that what is this function sine of a plus k times sine of a minus k. Then the product is added with plus 1. So for that, first we try to plot a special case, like thing k is equal to, sorry, for a general k where k is in a real number on real n, plus minus infinity to plus infinity. Think that a is equal to some particular value, let's say its value is 1 for the moment. Then sine of a plus k, which is sine of 1 plus k here, let's say. So if you plot the function, how it will look like? So we have k axis here. We are going to plot the function sine of a plus k, 1 plus k. So when k is a negative or lesser than minus 1, so when k is great, so sine of a plus k changes sign when k become minus 1. Before that, its sign is different, and after k is equal to minus 1, its sign is different. So minus 1 is a point that we need to locate. Sorry, yeah, so let's say this is minus 1. So before that, its value is negative. After that, value is positive. So this is sine of 1 plus k. Similarly, if you look at sine of 1 minus k, because we need sine of a plus k and sine of a minus k. So here we are particularly looking at the value a equal to 1. So what we are going to see is that now this function sine of 1 minus k changes sign when k is equal to plus 1. So let's say this is plus 1. So then before that its value is minus 1. Did I 1 minus k? Okay, sorry, I made a mistake. Before that its value is plus 1. When k is greater than 1, its value become minus 1. Okay, so I think that is clear. Now if you think that generally, if you have so here I have plotted the special case when a is equal to 1. Okay, before going to that, okay, now we can combine their product, like sine of 1 plus k times sine of 1 minus k. So what to do is that you just take the product between the left and right. So left we have this function and right we have this function. We just take the product. So the points minus 1 and plus 1 are the locations where the sign changes are happening. So before minus 1, sine of 1 plus k is actually negative 1 and the sine of 1 minus k is actually positive 1. So their product will be negative 1. So until this it is negative 1. Also after plus 1, sine of 1 plus k is positive 1 and sine of 1 minus k is negative 1. So their product is also negative after plus 1, but in between minus 1 and plus 1, both the functions are positive or plus 1, so the product will be plus 1. So this is how the function will look like, sine of 1 plus k times sine of 1 minus k. Now if you are adding, so what we want here is that it's not just sine of 1 plus k times 1 minus k. It's generally a can be any value, any real value. So if that is the case, instead of 1, if we have general a, the situation is not changed much. It's just that this rectangular shape is going to come in between minus a and plus a instead of minus 1 and plus 1. But the value is bounded between minus 1 and plus 1. The function value is bounded between plus 1 and minus 1. So I think that's clear. If you have any doubt in this section, you can ask me. I will try to explain again, or I will continue. So what we now got is that the function sine of a plus k times sine of a minus k will look something like this, that if you have minus a here and plus a here on the k axis, the function value is minus 1 here also, and here it is plus 1. So now what we want is that we need to so this is minus 1 and this is plus 1. So now what we want is that see, inside the integral you can see that we need to add plus 1 to this function, then only we need to take the integral. So we add plus 1 to the function, that is this function. This function will get shifted upwards by plus 1 unit. So after that this function will become like this. So we are shifting 1 unit upward. So wherever it was minus 1 becomes 0 now, and wherever it was plus 1 will become plus 2. So this is the function that is in the blue color that we want to integrate its value from minus infinity plus infinity here. Okay, so notice that this is just a rectangular function. Its name is actually rectangular function, rectangular of x with the width of, so it's actually x by 2a, width of 2a. You can see from minus a to plus a it have a width of 2a and height of 2. Okay, so that's what we are going to use here. So you see the area will be contributed only from the rectangular part where only it has the values. So just this area, that's the only part we are going to evaluate in this integral. This is just pi by 4 that's pi by 4 times, even though we are integrating from minus infinity to plus infinity, only minus a to plus a, the rectangle is contributing to the area, so that it's just the area of the rectangle. Its height is 2 times width is 2a, so it's basically pi a is the answer. So the integral we wanted, we got its value is pi a. So the question was asking to evaluate sin ax by x the whole square dx from minus infinity to plus infinity, and now we got its value is pi a. But I made a mistake, I think. In the question there was 0 to infinity, so in the lower limit was actually 0. So it's okay, for the moment I made a mistake. So if it is 0, then you know what to do, right? Because the function inside is actually even function, so that the integral will be just half of it. It's pi a by 2. So but option I don't have pi a by 2 because I didn't realize that I made a mistake. So I supposed to give pi a by 2 here in the option A, so which is the answer. It's not pi square a square by 4, so you know why, right? So that's how we need to do this integral. Any question in this? Any doubt? Is it clear or? So I guess it is clear. So I'll then move to the next problem.
Yes, sir, it is clear.
Okay, good. So find the Laplace transform of the function log t. So this is basically natural logarithm, the log with the base e in the function variable is t. So you need to find its Laplace transform in the s variables. So you can try for a minute, and then I will start doing. So anyway, I will write the expression that you need to evaluate from the basic principles. Just ln of Laplace transform of ln of t, which is ln t times e raised to minus st dt integral 0 to infinity. So it's just the basic definition of Laplace transform. Now we just need to figure out how to evaluate this integral. That's all. Yeah, we have one option here, whether this integral exists or not. Option D is also there. So while you try, you will know whether it exists or not, right? So anyway, I'll wait for a while. anyone got the answer, or is it exist, or okay, anyway, I will try to do it. So meanwhile, if you get the answer, you can just put it in the chat box so that we can then later see where it went wrong. Okay, so so this integral is I mean, we can do a product rule, but that's it's actually complicated process. So easier method is like a substitution. We can put st to a new variable, let's say it's x, so then s into dt is equal to dx, so that this integral become, so ln t will become ln of x by s, right, into e raised to minus st is just minus x into dt is dx by s, and the integration variable is now x, its value going to vary from, again, x is equal to 0 to x is equal to infinity, because just this is the rule, right? So now we can expand. So log of a by b is log a minus log b. That rule we can use here, log x minus log s, and see this s is actually a constant, so that we can take outside the integral into e raised to minus x dx. So now we split the integrals separately, like ln x into e raised to minus x dx, integral 0 to infinity, which is the first integral. Then the second integral is ln s, which is actually a constant in the second integral, because the integration variable is x, right? So that's why I took that also outside, into e raised to minus x dx. So 1 by s, this first integral does not contain any term from s, so it's actually a constant, and for the moment I just say it's actually minus gamma, where gamma, so it's actually a well-known integral. I don't know is it well-known, but it is actually well-defined integral to have a constant value. Its value is minus gamma, but gamma is Euler-Mascheroni constant. Its value is around 0.5771, I think. So the integral will converge to minus gamma, minus the second one is e raised to minus x. So that we can easily perform, right? Separately we can perform it. E raised to minus x dx, integral 0 to infinity is just e raised to minus x divided by minus 1, and apply the limit 0 to infinity. So it's just e raised to minus infinity minus e raised to minus 0 by minus 1. So that is just plus 1, right? So that's what I am going to do here. It's my ln s times 1. So that means minus gamma minus ln s the whole divided by s. That's solution. So which is option B actually. So now about gamma. So it's ln x times e raised to minus x dx, 0 to infinity, minus of that, which is equal to gamma. Okay, so which is approximately equal to 0.5771. Okay, the numerical value I have a little confusion, that you can check, but it's close to 0.577. So the thing is that this is also I think it's a transcendental number, like pi e, that you cannot express gamma in terms of rational numbers. So those things you can look up. So how it first appears is like you can have a function that is 1 by x, right? 1 by x, let's say y is equal to 1 by x is a function we are plotting. So we can approximate the area from 1 to, let's say, infinity, using the triangles, the rectangles here. the basic rule of integration. So what will you do is that the step size is h. So what you have to do is, so the specific value of gamma will appear if you use the step size of 1. So you will try to use the summation. It's like 1 by x equal to 1 to infinity, which is going to approximate this area. But the actual area we know, which is dx by x integral 1 to infinity, right? Now thing is that the difference between both, and you know this is the more than this one because we are approximating with this rectangle. So there is a excess area that we are losing, like these forms. So if you subtract them, that is a minus s, the actual area minus the approximate area, which is like dx by x integral 1 to infinity minus sigma x equal to 1 to infinity 1 by x. Remember that both of these integrals are diverging because the first one is, so let's say the last number I will say n commonly, and ln limit n tends to infinity, so that the first one is ln of n, right? The first integral. Second one, we know that the sum of reciprocals of the natural numbers. This is the harmonic series, right? Hn, I think. So both of them individually are diverging, like infinity minus infinity, but this limit actually exists. This value is gamma. You can check this. So basically these individual smaller areas that we left added over, we will get this particular constant gamma. So yeah, that's just a side note. So any question in this, any doubt, this problem?
Sir,
Yeah, yes.
the value of gamma can we find like performing this integral by any method?
Which one? This integral you are saying?
Yes, log x
Yeah,
e
yeah.
power minus x.
Yes, yeah, sure. So this is actually, so if you see the definition of gamma, that is this one here. So which is actually convergence rate is very slow. But the second definition, it's not actual definition, it's a consequence. So if you do some other operations, you will get into this expression, which is actually, see, the exponential is there, which is going to make it fast, like converge faster. So if you actually, you can numerically evaluate like 0 to, let's say, n ln x e raised to minus x dx. So it's I of n. So in the limit of n tending to infinity, this I of n is approaching gamma. So this you can numerically do, like you can use some integration method like Simpson's rule or a trapezoidal rule, whatever. You can numerically evaluate its values 0.57 something, that you can evaluate.
Okay, sir.
Okay. So any other question? Okay, I think that's clear. Then we'll move to the next question. So the Laplace transform of the error function. So options are given here. So you can try. Anyway, I will wait for a while, then I will start explaining. So one thing, so if you don't want me to wait, you can tell me so that I don't wait. I mean, I just hope that you can try, then parallelly I will explain how to do them. Okay. So anyway, I will define the error function. By the definition, error function is it's actually normalized with the number square root of 2 by pi, then integrated from 0 to t, the particular value, e raised to minus x square dx. So that's the error function. It has a complementary function, that is complementary error function, which is also, by definition, it is square root of 2 by pi t to infinity e raised to minus x square dx. And they have property error function of t plus error function conjugate, the complement of t is equal to 1, because they are added up to square root of 2 by pi, 0 to t, then t to infinity. It's like 0 to infinity e raised to minus x square dx. And you know this integral is actually square root of pi by 2. So basically they will cancel and you will get the value 1. So that's just a property of them. So we just want to evaluate its Laplace transform. So I suggest so not to use the basic definition of Laplace transform here. Try to use some property of Laplace transform. That's what going to help here. Any suggestion which property will help here? So if you have the Laplace transform of a function f of t is capital F of s, then the Laplace transform of its integral will be 1 by s times f of s. So that's a property going to help here, so that we can do this easily. So here the function f will be e raised to minus x square, because you see that by the definition the error function error function is actually an integral, right? So Laplace transform of that error function, which is square root of 2 by pi 0 to t e raised to minus x square dx. So the constant 2 by square root of pi we can take it outside. Then it's just Laplace transform of an integral 0 to t e raised to minus x square dx. So now see, it's an integral, so if we know just the Laplace transform of the function inside the integral, then it is easy, right? 2 by square root of pi 1 by s times Laplace transform of e raised to minus x square. So that's all. So we need to just evaluate e raised to minus x square, its Laplace transform. So Laplace transform of e raised to minus x square, it's actually should come in the table also. You can look into the table, but we can evaluate it. This is actually easier. E raised to minus x square times e raised to minus st by basic definition. Okay, sorry. Yeah, because we are using the variable x here, it's e raised to minus x square, e raised to minus xs dx 0 to infinity. This is just the definition. I am using the variable x instead of t. Okay, that's all. So now we combine the exponentials. That's e raised to minus x square plus sx dx. Like last class I have explained, there we can complete the squares, right? So we can write as x plus s by 2 the whole square minus s by 2 the whole square. I guess it's obvious to do that way. If you have doubts, stop me, I will explain that how to do that. So now we split the exponentials. E raised to minus x plus s by 2 the whole square times e raised to plus s by 2 the whole square dx. And see, this is actually a constant term that does not depend on the integration variable x, so we can take that outside. E raised to s square over 4 times e raised to minus x plus s by 2 the whole square dx, 0 to infinity. Now use a substitution, like it's actually a translation, x plus 2, sorry, x plus s by 2, let's say that's y, then dx is equal to dy. So e raised to s square by 4 into the integral become e raised to minus y square dy, where y goes from, because x is going from 0 to infinity, y will go from s by 2 to infinity plus s by 2, just let's say it's just infinity only. So now you see this is resembling the complementary error function, just that we don't have the normalization constant. You see that this is the definition of this is the definition of complementary error function with a 2 by square root of pi in front. So that means this particular expression that we can write square root of pi by 2, which is, because it's not there, we have to put a square root of pi by 2 in front, into raised to s square by 4 into error function complementary of s by 2. So that means we got what is the Laplace transform of. So go back to, this is the equation. If we know the Laplace transform of exponential minus x square, that we right now know, we can just substitute this in equation 1, so that we can get Laplace transform of error function of t by equation 1, which is 2 by square root of pi times 1 by s times Laplace transform of exponential of minus x square, that we right now know, which is square root of pi by 2 into e raised to s square by 4 into complementary error function of s by 2. Now see, this 2 by square root of pi and square root of pi by 2, they will cancel. So just e raised to s square by 4 by s complementary error function of s by 2, so which is the solution. So option C. So any question in this problem? Is it is this clear, or do you need to explain any part again? Okay, so I think this is clear. So we'll move to the next question. So it's this is to find the Laplace inverse of a function which is basically a ratio of polynomial functions, like s plus 3 divided by s plus 5 into s square plus 4s plus 5. So you can try yourself. I'll wait for a while, then we'll start. So you can use this method, like basically you have to use the properties of Laplace transform, like the shifting properties and all. Also the before that you have to do a partial fraction. Okay.
A equal to minus 1 by 5.
Okay. So once you evaluate A, B, and C, you can start doing an inverse Laplace transform using just the properties. So anybody got the answer? So I guess the partial fraction part is obvious, so I'm just skipping that. I'll just write the values of A, B, and C, then just the inverse Laplace transform. Okay. So the values of A, B, and C, A is minus 1 by 5, B is plus 1 by 5. So correct me if I'm wrong. I think this is the value. Then C is 4 by 5. Is it correct? Okay. So then we'll continue with this. So just Laplace inverse of, now the function we can write like minus 1 by 5 divided by s plus 5. Then so this is what I'm writing here. Okay, bs plus c, that's 1 by 5 times s plus 4 by 5 the whole divided by s square plus 4s plus 5. So because of the linearity I can split, also the constants I can take outside. So minus 1 by 5 times Laplace inverse of 1 by s plus 5 plus from both of these terms I am taking 1 by 5 outside. 1 by 5 times Laplace inverse of s plus 4 divided by s square plus 4s plus 5. First of all, this is inverse Laplace transform. So Laplace inverse of 1 by s minus a,
E power minus 5.
yeah, it's a e power minus
E
5
power
t,
minus
5t, because it's a raised to plus at. So because a here is minus 5, we will have this is Laplace inverse of 1 by s plus 5 is raised to minus 5t. So that part is over. Now we come on the right hand side. So Laplace inverse of s plus 4 divided by, so this denominator s square plus 4s plus 5, that we can write like completing the square, like we have to convert it to a form we already know. So a form we already know is s plus 2 the whole square plus 1, because we know that Laplace transform of sin at is equal to a divided by a square plus s square, and Laplace transform of cos at is equal to s divided by a square plus a square. So that's what we are going to use here. Before that, we need to do a shifting, because here it is not in terms of s, it's actually in terms of s square, sorry, s plus 2, that's what I want to say. So we do that like s plus 2, the numerator also we can split in terms of s plus 2. So it's s plus 2 the whole square plus 1 square. Now you see that this I can write it into, so because the function is now in terms of, so we have to use this property that Laplace inverse of s plus, sorry, s minus a,
first shifting theorem.
yeah, first shifting theorem, according to that,
Yes.
f of s minus a is equal to e raised to at times Laplace inverse of f of s. Is this correct?
E power minus 2t.
Okay. So according to that,
E power minus 2t.
yeah,
Inverse Laplace of s plus 2, s square plus 1.
Okay, yeah. So it's e raised to minus 2t times Laplace inverse of s plus 2
S
divided by
plus 2,
s square plus 1 square. Yeah.
separate again.
Yes. So we have to separate again. Like, so I think this s plus 2 is clear. It's not confused with
S
this
by
s plus
S
2.
square plus 1.
This 2 is coming here. Okay.
S plus S square plus 1 plus
1
2
divided
by
by
S.
s square plus 1 square times a constant 2 is there. That I am taking outside
Constant,
because we have to have this form because a is 1, right?
constant, but
Yeah.
S
So it's e raised to
cos
minus 2t
2t
times cos
cos
t plus 2 times
2 plus 2 into sin
sin
t.
t. So this is the Laplace transform of this part. Now we combine all of them with this minus 1 by 5. Also we have the other e raised to minus 5t of the left hand side. So if we combine everything, we will get option D as a solution. We can check. Okay. So any question? Is it clear or just partial fraction and just using the properties, shifting theorems and all. Then the some of the non inverse Laplace transforms. Okay, so I guess it is clear. So I'll move to the last problem.
Clear.
Yeah. So it's the inverse Laplace transform of the function hyperbolic sine alpha root s divided by s hyperbolic sine again root s, where alpha is less than 1 and greater than 0. So I don't have any options, and this is actually a miscellaneous problem. It requires some more time because I don't think there is an easy way to do this like the earlier one where we can use the non-integrals and non-inverse Laplace transforms. Here actually we need to use contour integration. So I want to explain that because I think in the assignment you have some questions related to this particular area, like using contour integral and all. So because we are running out of time, so I will just explain how to do this today, and next class anyway I will going to explain this properly. Okay, meanwhile you can use the idea that I am right now telling to solve the assignment problems. So by definition of inverse Laplace transform, is equal to f of s e raised to st ds integral c minus I infinity to c plus I infinity 1 by 2 pi I. So this is how we evaluate the inverse Laplace transform, where c should be such a way that c is a real number which should be greater than so c should be greater than all the singularities of this particular function that we have here. Okay, so this integral we are going to perform in the complex plane of s. Let's say the function here we have some singularities. The line, so c should be such a way that the line of integration is c minus I infinity to c plus I infinity. It should lie right of all these singularities. Let me use a different color to represent the singularities. Okay, so we have to integrate along this line. So here if you see, we so we will use the idea of contour integration, that completing this line with by closing using this arc, we will close the contour, and let's say the contour name, the complete contour I call it as gamma, and only the curved part, this I am calling as C, and the line I am calling as L. So it's like basically saying gamma is equal to the curved part plus the line part, and we want the integral that is sin h alpha root s divided by s sin h root s into e raised to st ds over the line only. So that is divided by 1 by 2 pi is going to give this Laplace inverse. But this we can write as let's say gamma is a closed contour including both C and L by the definition. So then the closed integral over the gamma of the same function we are integrating here also ds minus over the curved part only the same function we are integrating. So I think you guys have watched the lecture videos, that there also it is explained properly that the integral over this C, which can be shown, which will vanish to 0 using Jordan's lemma, and the integral over the contour, the entire closed contour, which can be shown to equal to 2 pi I times sum of the residues of this particular function over all the singular points. So that's what we are going to use here. It's like now we can say that Laplace transform of the function, which is this function, is equal to 1 by 2 pi I times this integral over the L, which from the residue theorem I can say it's 2 pi I divided by 2 pi I times sum of the residues. It's just basically equal to the sum of the residues of the function, which is sin h alpha root s divided by sin h root s times e raised to st over all the singular points. So here now our job is to find the singular points of this particular function. When the denominator vanishes, it is actually a singular point. Now you can say the denominator can vanish like two ways. S equal to 0 is a direct way of vanishing, thus 1 by s is making it singular. This exponential cannot be 0 or cannot be infinity, so that way that is not going to contribute to the singular parts. And next this numerator sin h is also a bounded quantity which cannot go to infinity in any way. I mean unless it is s itself is going to infinity. But the denominator here sin h root s is equal to 0 are also singular points, and you can see that for any real values of s it cannot happen, but imaginary values it can happen, because sin h I can also write is I into sin of I root s, which is equal to 0, or which means that because you know sin of I theta is equal to I sin h theta, the property of the relation relating the hyperbolic sine and the normal sine functions. So using that I can say it's a sin of I root s is equal to 0. So whenever a sine is 0, that means I root s should be equal to n pi for n equal to integers, right? So that means this is going to happen at root s is equal to minus I n pi, or s is equal to minus n square pi square. So when s equal to minus pi square, minus 4 pi square, minus 9 pi square, so these values are all singular points for this particular function. So we have one singular point as 0 and another singular point at these values. So if you plot the contour, let's say we have one singular point at 0, another is at minus pi square, another is at minus 4 pi square, another is at minus 9 pi square. So they are all separated in a square-wise manner. So we should choose the C such a way that C minus I infinity, C plus I infinity, to lie on the right of all the singularities. So we will choose any real positive number for C. doesn't matter. And now we close this loop to include all of the singularities. There are infinitely many singularities, right? Because it's actually minus pi square minus 4 pi, it's minus n square pi square. That's the general form for any natural number n. Now it will extend to infinity. So now we close the loop. So according to residue theorem, it says that the residue of the function about all the singular points, the singular points we have here, which are minus n square pi square and also 0. So that means the inverse Laplace transform that we want to evaluate is actually the residue of the function sin h alpha root s by s into sin h root s e raised to st at s equal to 0. The residue of the function sin h alpha root s by s into sin h root s e raised to st at s equal to minus n square pi square. This is for all n equal to 1 to infinity. So this is how we write the solution. So now how to find the residues? First of all, this is actually a simple pole. So if it is a simple pole, I guess the equation is already there in the lecture. So you can use, like, if the function is like this form, the residue of g of s by s minus a. At a it has a simple pole, right? So residue about s equal to a will be just g of a for any simple pole. So that's what we are going to use here. But so same applies here also. Here, but s equal to minus n square pi square is making this function a singular. That also simple pole that you can verify. If that's a simple pole, then you can again, but here actually it is not explicitly written in terms of s minus a. It's actually written in terms of like a general function which has let's say h of s, which has a singularity, simple pole at s equal to a. Then what you have to do is that you have to multiply with s minus a with the h of s, then taking the limit s tending to a is going to give the residue. That's what you can apply here for all values of s equal to n minus n square pi square. Then you do the summation, then add this value, you can get the solution. For this particular case, the solution will be look like alpha plus sigma n equal to 1 to infinity 2 into minus n the whole raised to n by n pi sine of alpha n pi into exponential of minus n square pi square t. So any question in this, I mean, I didn't solve it properly, but the method, I think, is that clear? So if you have any doubt, please ask. So because you have some assignments related to this kind of problem, so you can try yourself to do the assignment. Anyway, next week I'll try to explain this properly. Okay, so if you don't have any doubt, we'll end today's session. So next week we'll meet same time 3 to 4. Okay.
Thank you, sir.
Okay.